Okay, so for example one, it's not a pretty simple question. A car travels 35 miles per hour for 4 hours. How far does the car go? Car travels 35 miles an hour for 4 hours. How far does the car go? So this is not bad at all. It's just distance equals rate times time, right? So all you got to do is take the 35 miles an hour times the 4 hours. So 140 miles. Makes sense, right? If you go 35 miles an hour for 4 hours, then you're going to end up going 140 miles. Okay, so this is a fact that we need to keep in mind. Distance equals rate times time. Okay, now, let's say you throw a ball 60 miles an hour while riding on a train going 70 miles an hour. So you've got this train, right? And you're standing on the train, and the train is traveling 70 miles an hour. And you throw the ball set 60 miles an hour, right? So my question is, how fast will the ball go relative to the ground? How fast will the ball go relative to the ground? So you're going 70, right? You throw the ball 60. So how fast is the ball going relative to the ground? 130 miles an hour, right? Because it's already going 70 even before you throw it. But relative to the train, the ball's going 60 miles an hour, right? So notice I'm using the word relative, right? And then I'm using the word relative because it makes sense, but also that means theory of relativity may come up, right? All right, so yes, it comes up right now. It's a great segue. It is a fact that nothing can go faster than the speed of light. Light is really, really fast. I'm sure you've noticed that when you turn a light on in a room. It's at the other side of the room right away. Almost instantly. It seems like it's instant, but it's not. It takes some time to get to the other side of the room. But it's so fast that we don't even notice. Okay, so the speed of light is really, really fast. And on top of that, nothing can go faster than that. Nothing can go faster than the speed of light. This is part of Einstein's theory of relativity. It's impossible to go faster than the speed of light. Okay, and just so you know, the speed of light is 299,792,458 meters per second. So for the purposes of our discussion, we're going to probably round this off to 300 million, just so it's easier to work with. But this is the speed of light. Okay. So nothing can go faster than that. That's as fast as anything can go. So now, let's say you're back on your train going 70 miles an hour. and you have a flashlight. And the flashlight, you turn it on. So how fast is the light going relative to the train? Turn a flashlight on. And then how fast is the light going relative to the train? So the answer is 299 million, yada, 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 meters per second, right? Okay, so then how fast is it going relative to the ground? $299,700,000 plus 70, right? No, because nothing can go faster than the speed of light. Okay, so here's the quandary. Here's the quandary. The ball that we throw is going 60 miles an hour relative to the train, but 130 miles an hour relative to the ground, right? But the light is going the same speed relative to the train and the ground, because nothing can go faster than the speed of light. So I can't add 70 to this, right? Because nothing can be added to this. So it was an additive relationship when the speeds were small, but somehow it's not when the speeds are the speed of light. That's a problem. There's a dissonance there. There's a quandary there, right? Okay, so Einstein came to this fact, and then he realized that there was a conflict if this fact was true. So he had to solve that conflict somehow. Okay, so here, now we're going to think some more. So Einstein never did any actual experiments. He did what he called thought experiments. He just thought about stuff in his head, and then later on we verified that they were true. He didn't worry about that, though. He just knew they were true somehow by thinking. Okay, so let's say here's one of his thought experiments. So this is a thought experiment. So now we've got, here's the train car, right? And there's a person in there. Sorry, let's say the train car is 600 meters tall. So it's a pretty tall train car. And there's a person down here with a flashlight. And there's a mirror up here on the roof of the train car, right? And let's say the train's not moving. So since the train's not moving, the person turns the flashlight on, the light goes up to the mirror and then bounces back down, right? How long does it take the light to go up to the mirror and bounce back down? Four seconds, right? We're going to round this off to 300 million. So if it goes 300 million meters each second, it's going to take 2 seconds to go up to the mirror, and then another 200 seconds to come back down, right? So here's what I'm doing. I'm doing distance equals rate times time, and I'm saying, okay, it has to travel this many meters to go up and down, right? and it's traveling at 300 million meters per second or so. So I just divided both sides by 300 million. So it's going to take 4 seconds. Okay, so now, let's say instead of the train not moving, now the train is moving. Okay, so the train starts out here, and it ends up here, right? And there's somebody off in the distance watching this, and this train has a glass side. Okay, so the person inside the train can't, it's a one-way mirror, so the person can't see outside. And the person inside the train doesn't know if the train is moving or not, because it's got really, really smooth traveling power, right? Okay, so this is all a thought experiment, right? This is what we do when we're trying to think. Okay, so this person thinks the light traveled this far. This person doesn't know the train is moving, so thinks the light went straight up and came straight down, right? So this person thinks that it took 4 seconds. But over here, the outside observer, relative to the ground, this person inside still shines the light, but what happens is the light actually travels in this kind of a path, right? To the person outside, they don't see a light go straight up and down. They see the light also go sideways. The person inside the train thinks the light's going straight up and down. But the observer outside the train, sees the light go up, hit the top of the mirror, and come down in an arc path, right? Is everybody okay with that? That's the hardest thing so far. You see why the person outside the train sees the light go in this type of a path. Yeah?
So would it be like a straight line?
Maybe a straight line. Yeah, it could be. Yeah, I'd have to think more about that. But it's definitely not straight up and down. That's all we need for our thought experiment. Is everybody okay with that? Okay, so this distance here is longer than 1.2 billion meters, right? Because straight up and down is 1.2 billion meters. So if it's going to go up and then down, sideways, it's going to be bigger than this. So I don't know what it is. It depends on how fast the train's going, right? But it's going to be bigger than 1.2 billion. So let's just round it off to a nice 1.6 billion. Just a saying. And we know it's longer. So let's say that the distance is 1.6 billion. No, I'm sorry. I really want to make it 1.5. I'm just making. Why not? You know, I can do whatever I want. It's after the AP test, right? So it doesn't matter if I'm accurate at this point. Okay, so all I'm saying is that this number, this distance, is larger for the observer outside the train as opposed to the observer inside the train. Okay, but the rate is what? It's the speed of light. So it doesn't change regardless of the observer. So it's still 300 million, right? So check this out. For the person outside the train, 5 seconds went by. But for the person inside the train, 4 seconds went by. If the speed of light is going to be constant, regardless of the observer, then time has to change, depending on the observer. Uh-oh. You with me? Do you see why time has to be different? If this stays the same, time has to be different. So this person is traveling faster, right? Because they're in the train. Whereas the person on the ground is traveling slower. So if you're traveling faster, you experience less time than someone who is not traveling very fast. So here is the fact. This is a fact. As you travel faster, you experience less time. This is a fact. They have verified it. Well, Einstein just decided it had to be true and wrote it down. He didn't verify. Since then, they have verified this. It is true that if you travel faster, you experience less time. So what they've done is they've sent a clock, a very accurate clock, that is synchronized with another very accurate clock here on Earth. They've sent it up in orbit. And then they've orbited that clock for a long period of time. And then they've seen, and the clocks are different. The clock that was traveling faster in orbit does experience less time than the clock here on Earth that is not orbiting. Hold up. So this is true. If you travel faster, you do experience less time. So especially if you go really fast. If you go half the speed of light, you experience a fair number less time. There's a formula. I'm about to show you the formula for how much this shortens. It's crazy. They got it. They know what it is. I don't know who they is, but... Yes. Okay. I'll figure it out eventually after I usually wait and see. I'll let you not pay attention while I'm erasing.
He's trying to do fast.
Come on. Okay. So T0 equals T times 1 minus V over C squared to the 1/2 power. And, okay, so there's the formula. And what does C stand for? Speed of light. So you've heard E equals mc squared. C is what the variable that Einstein used for the speed of light. So that's true in this formula. C is the speed of light. And V is the velocity that the thing is going. So then let's use 300 million for our C. If this is 150 million, then this fraction will be a half, right? So if you're going 150 million, then you'll be going half the speed of light. Okay, so now we're going to ask some questions. You are traveling half the speed of light. What is this, example 2? You know, when I did, I don't have to be accurate. What is this, example 2? Okay, so you are traveling half the speed of light. How long does 1 year seem to you? So you are traveling half the speed of light. How long does 1 year for a person on Earth seem to you? So someone's here on Earth, and they send you off in a spaceship, and you travel at half the speed of light for what they think is a year. But you're going faster than them, right? So we want to know, how much time do you experience? Okay? So we're going to use this formula right here. This formula will tell us. So T is the time that one person experiences. So in this case, 1 year. So T0, time for the other person traveling half the speed of light, is 1 times 1 minus. And since we're going half the speed of light, this fraction will be a half. So it's really not that complicated of a formula. That's kind of amazing. So you take 1/2 and square it. That's a fourth, right? Then you take 1 minus a fourth, and you get 3/4. So I got 1 times 3/4 to the 1/2 power. So all I got to do is take the square root of 3/4 and multiply it by 1, and I got my answer, right? So 0.75 square rooted. So I'll round to 3 decimal places. That's 0.866. This one was in years, right? So this 0.866 is in years. So let's change that to months just to so we can get an idea. 0.866 times 12 will give us the number of months. So it's about 10 months. So let me make sure you understand what's going on here. You're on Earth. You send somebody away in a spaceship. They travel at half the speed of light for a year. They come back and they are certain that 10 months went by. And they're correct that 10 months for them went by. They only aged 10 months. You aged a year. They aged 10 months. It is a fact that 10 months went by.
How do birthdays work then?
Yeah, it gets complicated, doesn't it? It gets complicated. They didn't get their Christmas presents, and so let's say you're traveling 3/4 the speed of light. So this is part B. Let's say instead you're traveling 3/4 the speed of light. So now you build a spaceship that can go even faster, and you send them away at 3/4 the speed of light for a year, right? So now T0 equals 1 year that you think happened times 1 minus 3/4 squared to the 1/2 power. So 3/4 squared, 1 minus that, so 0.4375 to the 1/2 power, 0.661. So you experienced 1 year, but they only experienced 0.661 years. So let's multiply that by 12. So that's about around 8 months. So we said if you go faster, you experience less time. So if you only went half the speed of light, you experience 10 months. But if you can go 3/4 the speed of light, your time shortens even more, and you only experience 8 months. So now part C is so for part C, let's say you do travel at speeds that approach the speed of light. How much time do you experience? So this is the first time I've gotten into calculus at all. This word approach, right, sounds like a limit. Sorry to bring up bad memories from yesterday, but I gave you a break for most of the period. Okay, so I'm going to take the limit as v approaches the speed of light, right? Of this 1 times 1 minus v over c squared to the 1/2 power. So as v approaches c, I can just do a bunch of limit laws. And as v approaches c, then basically that limit is c. And then c divided by c is 1. 1 squared is 1. 1 minus 1 is 0. I've got the wrong thing here. It's supposed to be the 1/2 power. And the square root of 0 is 0. So as you approach the speed of light, you experience less and less time. So, and the limit of that is that you experience 0 time. So now I'm not willing to go here, but let's say you did travel the speed of light, then time for you would stop. So you could somehow accelerate yourself to the speed of light, which is a difficult thing to do. Then somehow your time would stop. The reason it's a difficult thing to do is, I didn't mention this, but as you increase your speed, your mass increases and your length. And so it's very difficult to speed up then because your mass keeps increasing. Yes, sir?
So if you did manage to go faster than the speed of light, would you like Benjamin Button or something? Like
Maybe theoretically, yes, but this goes beyond what is true.
Right.
You know, it is a fact, at least under current understandings, which have been verified to a large extent, that you can't go faster than the speed of light. And in fact, you can't even go the speed of light if you have a mass, because your mass will approach infinity as you approach the speed of light. So, but yes, theoretically, absolutely. Yes, yes. So TJ, thank you.
Wasn't there also something about mass affecting time as well? Like if you are around a massive object?
I think it's just because the large massive object speeds you up.
Okay.
Because the gravity, it has such a large gravity that it accelerates you.
Yeah.
And thus it does affect your time, but indirectly in some ways, yes. You had a question, Brandon?
Oh, I was just wondering, you know how like they say the universe is expanding or whatever?
Yes.
I don't know if that was any way related because
Well, certainly we are traveling at a fairly rapid speed around the sun, and the sun around the center of the galaxy, but still nowhere near the speed of light. And so because of that, our mass and our time is not affected very much. You know, this fraction here of, even if we were going 30,000 miles an hour, that's a tiny fraction of c. And so it's really a negligible effect. But you're right, as we expand, we're going a constant velocity, we're not accelerating. So the effect is a constant as far as what you're asking, as far as I know. Yeah. All right, thanks for listening.